Bueno, el siguiente ponente es profesor Stephen Hawking.
Nowhere is this more true than in the case of black holes. Black holes are stranger than anything dreamed of by science fiction writers, but they are firmly matters of science fact. Not that science fiction was slow to climb on the bandwagon after black holes were discovered. I remember going to the premiere of the Walt Disney film, The Black Hole, in the 1970s. It was about a spaceship that was sent to investigate a black hole that had been discovered. It wasn't a very good film, but it had an interesting ending. After orbiting the black hole, one of the scientists decides the only way to find out what is going on is to go inside. So he gets into a space probe and dives into the black hole. After a screenwriter's depiction of hell, he emerges into a new universe. This is an early example of the science fiction use of a black hole as a wormhole, a passage from one universe to another, or back to another location in the same universe. Such wormholes, if they existed, would provide shortcuts for interstellar space travel, which otherwise would be pretty slow and tedious if one had to keep to the Einstein speed limit and stay below the speed of light. Let me describe briefly how a black hole might be created. Imagine a star with a mass 10 times that of the Sun. During most of its lifetime of about 1 billion years, the star will generate heat at its center by converting hydrogen into helium. The energy released will create sufficient pressure to support the star against its own gravity, giving rise to an object with a radius about 5 times the radius of the Sun. The escape velocity from the surface of such a star would be about 1,000 kilometers per second. That is to say, an object fired vertically upward from the surface of the star, with a velocity of less than 1,000 kilometers per second, would be dragged back by the gravitational field of the star, and would return to the surface. Whereas an object with a velocity greater than that would escape to infinity. When the star had exhausted its nuclear fuel, there would be nothing to maintain the outward pressure, and the star would begin to collapse because of its own gravity. As the star shrank, the gravitational field at the surface would become stronger, and the escape velocity would increase. By the time the radius had got down to 30 kilometers, the escape velocity would have increased to 300,000 kilometers per second, the velocity of light. After that time, any light emitted from the star would not be able to escape to infinity, but would be dragged back by the gravitational field. According to the special theory of relativity, nothing can travel faster than light, so that if light cannot escape, nothing else can either. The result would be a black hole, a region of space-time from which it is not possible to escape to infinity. The boundary of the black hole is called the event horizon. It corresponds to a wavefront of light from the star that just fails to escape to infinity, but remains at the Schwarzschild radius, 2gm over c squared, where g is Newton's constant of gravity, m is the mass of the star, and c is the velocity of light. For a star of about 10 solar masses, the Schwarzschild radius is about 30 kilometers. There is now fairly good observational evidence to suggest that black holes of about this size exist in double star systems, such as the X-ray source known as Cygnus X1. The X-rays are given off by matter falling into the black hole. There is also a massive black hole 4.31 million times the mass of the Sun at the center of our galaxy. The video shows the orbits of stars in a gas cloud near the black hole. It is thought there are massive black holes at the centers of most galaxies. Important investigations in the field of stellar mass black holes have been done here in the Canary Islands. For example, The first observational evidence that supernova explosions may create stellar mass black holes has been done here by the director of the Starmus Festival, Garrick Israelian, and his team. There might also be quite a number of very much smaller black holes scattered around the universe, formed not by the collapse of stars, but by the collapse of highly compressed regions in the hot dense medium, that are believed to have existed shortly after the Big Bang, in which the universe originated. Such primordial black holes are of greatest interest for the quantum effects I shall describe here. A black hole weighing 1 billion tons, about the mass of a mountain, would have a radius of about 10 to the minus 13 centimeters, which is the size of a neutron or a proton. It could be in orbit either around the Sun, or around the center of the galaxy. Light doesn't really consist of particles, rather like cannonballs, that could be slowed down by gravity, and made to fall back on the star. A famous experiment, carried out by two Americans, Michelson and Morley, in 1887, showed that light always traveled at a speed of 186,000 miles a second, no matter where it came from. How then could gravity slow down light, and make it fall back? This was impossible, according to the then accepted ideas of space and time. But in 1915, Einstein put forward his revolutionary general theory of relativity. In this, space and time were no longer separate and independent entities. Instead, they were just different directions in a single object called space-time. His space-time was not flat, but was warped and curved by the matter and energy in it. In order to understand this, consider a sheet of rubber, with a weight placed on it, to represent a star. The weight will form a depression in the rubber, and will cause the sheet near the star to be curved, rather than flat. If one now rolls marbles on the rubber sheet, their paths will be curved, rather than being straight lines. In 1919, a British expedition to West Africa looked at light from distant stars that passed near the Sun during an eclipse. They found that the images of the stars were shifted slightly from their normal positions. This indicated that the paths of the light from the stars had been bent by the curved space-time near the Sun. General relativity was confirmed. Consider now placing heavier and heavier, and more concentrated weights on the rubber sheet. they will depress the sheet more and more. Eventually, at a critical weight and size, they will make a bottomless hole in the sheet that particles can fall into, but nothing can get out of. What happens in space-time according to general relativity is rather similar. A star will curve and distort the space-time near it more and more, the more massive and more compact the star is. If a massive star that has burned up its nuclear fuel cools and shrinks below a critical size, it will quite literally make a bottomless hole in space-time that light can't get out of. Such objects were given the name black holes by the American physicist John Wheeler, who was one of the first to recognize their importance and the problems they pose. The name caught on quickly. It suggested something dark and mysterious, but the French, being French, saw a more risky meaning. For years, they resisted the name trou noir, claiming it was obscene. But that was a bit like trying to stand against the weekend, another Franklin. In the end, they had to give in. Who can resist a name that is such a winner? From the outside, you can't tell what is inside a black hole. You can throw television sets, diamond rings, or even your worst enemies into a black hole, and all the black hole will remember is the total mass and the state of rotation. John Wheeler called this, a black hole has no hair. To the French, this just confirmed their suspicions. A black hole has a boundary, called the event horizon. It is where gravity is just strong enough to drag light back and prevent it escaping. Because nothing can travel faster than light, everything else will get dragged back also. Falling through the event horizon is a bit like going over Niagara Falls in a canoe. If you are above the falls, you can get away if you paddle fast enough, but once you are over the edge, you are lost. There's no way back. As you get near the falls, the current gets faster. This means it pulls harder on the front of the canoe than the back. There's a danger that the canoe will be pulled apart. It is the same with black holes. If you fall towards a black hole feet first, gravity will pull harder on your feet than your head, because they are near the black hole. The result is, you will be stretched out longwise and squashed in sideways. If the black hole has a mass of a few times our sun, you would be torn apart and made into spaghetti before you reached the horizon. However, if you fell into a much larger black hole, With a mass of 1,000,000 times the Sun, you would reach the horizon without difficulty. So, if you want to explore the inside of a black hole, choose a big one. There is a black hole of about 4 million solar masses at the center of our Milky Way galaxy. Although you wouldn't notice anything particular as you fell into a black hole, someone watching you from a distance would never see you cross the event horizon. Instead, you would appear to slow down and hover just outside. You would get dimmer and dimmer, and redder, until you were effectively lost from sight. As far as the outside world is concerned, you would be lost forever. The first hint that there might be a connection between black holes and thermodynamics came with a mathematical discovery in 1970. That the surface area of the event horizon, the boundary of a black hole, has the property that it always increases when additional matter or radiation falls into the black hole. Moreover, if two black holes collide and merge to form a single black hole, the area of the event horizon around the resulting black hole is greater than the sum of the areas of the event horizons around the original black holes. These properties suggest that there is a resemblance between the area of the event horizon of a black hole and the concept of entropy in thermodynamics. Entropy can be regarded as a measure of the disorder of a system, or equivalently, as a lack of knowledge of its precise state. The famous second law of thermodynamics says that entropy always increases with time. The analogy between the properties of black holes and the laws of thermodynamics was extended by James Bardeen of the University of Washington, Brandon Carter, who is now at the Meudon Observatory, and me. The first law of thermodynamics says that a small change in the entropy of a system is accompanied by a proportional change in the energy of the system. The fact of proportionality is called the temperature of the system. Bardeen, Carter, and I found a similar law relating the change in mass of a black hole to a change in the area of the event horizon. Here the factor of proportionality involves a quantity called the surface gravity, which is a measure of the strength of the gravitational field at the event horizon. If one accepts that the area of the event horizon is analogous to entropy, then it would seem that the surface gravity is analogous to temperature. The resemblance is strengthened by the fact that the surface gravity turns out to be the same at all points on the event horizon, just as the temperature is the same everywhere in a body at thermal equilibrium. Although there is clearly a similarity between entropy and the area of the event horizon, it was not obvious to us how the area could be identified as the entropy of a black hole. What would be meant by the entropy of a black hole? The crucial suggestion was made in 1972 by Jacob Bekenstein, who was then a graduate student at Princeton University and is now at the Hebrew University of Jerusalem. It goes like this. When a black hole is created by gravitational collapse, it rapidly settles down to a stationary state that is characterized by only three parameters: the mass, the angular momentum, and the electric charge. Apart from these three properties, the black hole preserves no other details of the object that collapsed. This conclusion, known as the theorem, "a black hole has no hair," was proved by the combined work of Carter Werner Israel of the University of Alberta, David Robinson of King's College, London, and me. The no-hair theorem implies that a large amount of information is lost in a gravitational collapse. For example, the final black hole state is independent of whether the body that collapsed was composed of matter or antimatter, and whether it was spherical or highly irregular in shape. In other words, a black hole of a given mass, angular momentum, and electric charge could have been formed by the collapse of any one of a large number of different configurations of matter. Indeed, if quantum effects are neglected, the number of configurations would be infinite, since the black hole could have been formed by the collapse of a cloud of an indefinitely large number of particles of indefinitely low mass. The uncertainty principle of quantum mechanics implies, however, that a particle of mass m behaves like a wave of wavelength h over mc, where h is Planck's constant, and c is the velocity of light. In order for a cloud of particles to be able to collapse to form a black hole, it would seem necessary for this wavelength to be smaller than the size of the black hole that would be formed. It therefore appears that the number of configurations that could form a black hole of a given mass, angular momentum, and electric charge, although very large, may be finite. Bekenstein suggested that one could interpret the logarithm of this number as the entropy of a black hole. The logarithm of the number would be a measure of the amount of information that was irretrievably lost during the collapse, through the event horizon when a black hole was created. The apparently fatal flaw in Bekenstein's suggestion was that if a black hole has a finite entropy that is proportional to the area of its event horizon, it also ought to have a finite temperature, which would be proportional to its surface gravity. This would imply that a black hole could be in equilibrium with thermal radiation at some temperature other than zero. Yet according to classical concepts, no such equilibrium is possible, since the black hole would absorb any thermal radiation that fell on it, but by definition would not be able to emit anything in return. This paradox remained until early in 1974, when I was investigating what the behavior of matter in the vicinity of a black hole would be, according to quantum mechanics. To my great surprise, I found that the black hole seemed to emit particles at a steady rate. Like everyone else at that time, I accepted the dictum that a black hole could not emit anything. I therefore put quite a lot of effort into trying to get rid of this embarrassing effect. It refused to go away, so that in the end I had to accept it. What finally convinced me it was a real physical process was that the outgoing particles have a spectrum that is precisely thermal. The black hole creates and emits particles and radiation, just as if it were an ordinary hot body, with a temperature that is proportional to the surface gravity, and inversely proportional to the mass. This made Bekenstein's suggestion that a black hole had a finite entropy fully consistent, since it implied that a black hole could be in thermal equilibrium at some finite temperature other than zero. Since that time, the mathematical evidence that black holes can emit thermally has been confirmed by a number of other people with various different approaches. One way to understand the emission is as follows. Quantum mechanics implies that the whole of space is filled with pairs of virtual particles and antiparticles that are constantly materializing in pairs, separating, and then coming together again and annihilating each other. These particles are called virtual because, unlike real particles, they cannot be observed directly with a particle detector. Their indirect effects can nonetheless be measured, and their existence has been confirmed by a small shift, the Lamb shift, they produce in the spectrum of light from excited hydrogen atoms. Now, in the presence of a black hole, one member of a pair of virtual particles may fall into the hole, leaving the other member without a partner with which to annihilate. The forsaken particle or antiparticle may fall into the black hole after its partner, but it may also escape to infinity, where it appears to be radiation emitted by the black hole. Another way of looking at the process is to regard the member of the pair of particles that falls into the black hole, the antiparticle say, as being really a particle that is traveling backward in time. Thus the antiparticle falling into the black hole can be regarded as a particle coming out of the black hole, but traveling backward in time. When the particle reaches the point at which the particle-antiparticle pair originally materialized, it is scattered by the gravitational field, so that it travels forward in time. A black hole of the mass of the Sun would leak particles at such a slow rate, it would be impossible to detect. However, there could be much smaller mini black holes. These might have formed in the very early universe, if it had been chaotic and irregular. A black hole of the mass of a mountain would give off X-rays and gamma rays at a rate of about 10 million megawatts, enough to power the world's electricity supply. It wouldn't be easy, however, to harness a mini black hole. You couldn't keep it in a power station, because it would drop through the floor and end up at the center of the Earth. About the only way would be to have the black hole in orbit around the Earth. People have searched for many black holes of his mass, but have so far not found any. This is a pity, because if they had, I would have got a Nobel Prize. Another possibility, however, is that we might be able to create micro black holes in the extra dimensions of space-time. According to some theories, the universe we experience is just a 4-dimensional surface in a 10 or 11-dimensional space. We wouldn't see these extra dimensions, because light wouldn't propagate through them, but only through the 4 dimensions of our universe. Gravity, however, would affect the extra dimensions, and would be much stronger than in our universe. This would make it much easier to form a little black hole in the extra dimensions. It might be possible to observe this at the LHC, the Large Hadron Collider, at CERN, in Switzerland. This consists of a circular tunnel, 27 kilometers long. 2 beams of particles travel round this tunnel in opposite directions, and are made to collide. Some of the collisions might create micro black holes. These would radiate particles in a pattern that would be easy to recognize. So, I might get a Nobel Prize, after all. As particles escape from a black hole, the hole will lose mass and shrink. This will increase the rate of emission of particles. Eventually, the black hole will lose all its mass and disappear. What then happens to all the particles and unlucky astronauts that fell into the black hole? They can't just re-emerge when the black hole disappears. The particles that come out of a black hole seem to be completely random, and to bear no relation to what fell in. It appears that the information about what fell in is lost, apart from the total amount of mass and the amount of rotation. But if information is lost, this raises a serious problem that strikes at the heart of our understanding of science. For more than 200 years, we have believed in scientific determinism, that is, that the laws of science determine the evolution of the universe. This was formulated by Laplace as, if we know the state of the universe at one time, the laws of science will determine it at all future and past times. Napoleon is said to have asked Laplace how God fitted into this picture. Laplace replied, "Sire, I have not needed that hypothesis." I don't think that Laplace was claiming that God didn't exist. It is just that he doesn't intervene to break the laws of science. That must be the position of every scientist. A scientific law is not a scientific law if it only holds when some supernatural being decides to let things run and not intervene. In Laplace's determinism, one needed to know the positions and speeds of all particles at one time in order to predict the future. But according to the uncertainty relation, the more accurately you know the positions, the less accurately you can know the speeds, and vice versa. In other words, you can't know both the positions and the speeds accurately. How then can you predict the future accurately? The answer is that although one can't predict the positions and speeds separately, one can predict what is called the quantum state. This is something from which both positions and speeds can be calculated to a certain degree of accuracy. We would still expect the universe to be deterministic, in the sense that if we knew the quantum state of the universe at one time, the laws of science should enable us to predict it at any other time. If information were lost in black holes, we wouldn't be able to predict the future, because a black hole could emit any collection of particles. It could emit a working television set, or a leather-bound volume of the complete works of Shakespeare, though the chance of such exotic emissions is very low. It is much more likely to be thermal radiation, like the glow from red-hot metal. It might seem that it wouldn't matter very much if we couldn't predict what comes out of black holes. There aren't any black holes near us. But it is a matter of principle. If determinism breaks down with black holes, it could break down in other situations. There could be virtual black holes that appear as fluctuations out of the vacuum, absorb one set of particles, emit another, and disappear into the vacuum again. Even worse, if determinism breaks down, we can't be sure of our past history either. The history books in our memories could just be illusions. It is the past that tells us who we are. Without it, we lose our identity. It was therefore very important to determine whether information really was lost in black holes, or whether in principle it could be recovered. Many people felt that information should not be lost, but no one could suggest a mechanism by which it could be preserved. The arguments went on for years. Finally, I found what I think is the answer. It depends on the idea of Richard Feynman that there isn't a single history, but many different possible histories, each with their own probability. In this case, there are two kinds of history. In one, there is a black hole into which particles can fall, but in the other kind, there is no black hole. The point is that from the outside, one can't be certain whether there is a black hole or not. So there is always a chance that there isn't a black hole. This possibility is enough to preserve the information, but the information is not returned in a very useful form. It is like burning an encyclopedia. Information is not lost if you keep all the smoke and ashes, but it is difficult to read. Kip Thorne and I had a bet with John Preskill that information would be lost in black holes. When I discovered how information could be preserved, I conceded the bet. I gave John Preskill an encyclopedia. Maybe I should have just given him the ashes. What does this tell us about whether it is possible to fall in a black hole and come out in another universe? The existence of alternative histories with black holes suggests this might be possible. The hole would need to be large, and if it was rotating, it might have a passage to another universe. But you couldn't come back to our universe. So, although I'm keen on space flight, I'm not going to try that. The message of this lecture is that black holes ain't as black as they are painted. They are not the eternal prisons they were once thought. Things can get out of a black hole, both to the outside, and possibly to another universe. So, if you feel you are in a black hole, don't give up. There's a way out.
Hay una silla acá.
Una silla para ti. Para ti.
Okay. I'll get the lecture up for Steve and the next question.
Gracias a todos. Había una competición, un concurso llamado Pregunta a Hawking. Entonces, miles de personas y sobre todo los delegados enviaban preguntas y nosotros elegimos unos 30, 40 más interesantes y enseñamos a profesor Hawking para que él elige las preguntas más interesantes. Entonces, ahora tenemos los ganadores de este concurso que van a recibir ese libro con la huella, con la firma de profesor Hawking. Y van a hacer sus preguntas y profesor Hawking va a contestar aquí, ahora. Entonces, primero es Felipe Macías.